We will now announce the winners of the 2024 CodeX Prize. And our very own Harry Certain, who was the first fellow of CodeX in 2006, will be announcing the winners. So Harry, come on up.
Well, thank you, Roland. As Roland said, I'm Harry Certain. I'm Associate Director here at the Stanford CodeX Center. Fellow 18 years ago, which is strange because I'm only 24. Not sure how the math works out. And also a law professor at the University of Colorado. Before I announce the CodeX Prize winner, I want to first thank all the people who worked so hard to put FutureLaw together. You've not seen behind the scenes, but amazing people like Roland Vogel, Megan Ma, Oliver Goodenough, Mike Genesreth, and the program group, Giselle Brown and Maria, have been working for weeks and weeks to make this thing possible. So please thank our amazing CodeX crew here. So it is my great honor to present the 2024 CodeX Prize to two individuals who have made foundational contributions to the field of AI and law, Thorne McCarty and Ann Gardner. These pioneers have inspired countless people, including myself, with their groundbreaking work and visionary insights. They saw the potential of AI and law way back before almost anyone else did, back in the 1970s and 1980s. They are not able to join us in person, but they will be joining us by Zoom and by video shortly. But before we have some remarks for them, let me tell you a little bit about our recipients. Thorne McCarty is Professor of Computer Science and Law Emeritus at Rutgers University. He's a graduate of Harvard Law School and Yale University, where he studied mathematics and philosophy. Thorne helped kickstart fundamental ideas in the field of AI and law and legal reasoning with his seminal publication, Taxman, an experiment in artificial intelligence and legal reasoning, in the Harvard Law Review in 1977. This work was one of the first attempts to formalize aspects of law, specifically tax law, in a form that computers could reliably process. This had a tremendous impact on the thinking of all of the folks in the field of AI and law. And then Thorne went on to an incredible interdisciplinary career at the intersection of computer science and law in academia. Our second recipient, Ann Gardner, is the epitome of a computer and law pioneer. She obtained both her law degree and her PhD here at Stanford University. And Ann went on to produce a series of landmark works, including her highly influential book, An Artificial Intelligence Approach to Legal Reasoning, published in 1987. And in this research, she explored some of the fundamental ideas that we still use today, ideas such as open texture and subjectivity among legal standards, theories of representing legal rules in computable form. Ann's ideas have had an enduring impact on the field of law and continue to shape our understanding of how AI can be applied to legal reasoning. Please join me in congratulating Ann and Thorne, and they're going to give us a few remarks.
Mike Genesreth invited me to say something about what I'm working on these days and how it is related to my work on Taxman many years ago. It happens that this work is closely related to what you will be discussing in the session after lunch on neurosymbolic AI. So here is an overview: probability, geometry, logic. As everyone knows, the first wave of AI was based on logic. The second wave was based on probability. And there have been a number of attempts over the years to combine the two into a single formalism. What is novel here is geometry. The geometric model is built on top of the probabilistic model, and the logic is built on top of the geometry. The key issue then is how to construct the interfaces. Also, we want to extend this stack recursively so that the logic supports another probabilistic layer. I'm writing 3 articles on this. The first was just published in AMAI, Annals of Mathematics and Artificial Intelligence. The third is still an incomplete draft, but I've distributed copies to several people for initial comments, and I hope to finish it in the next couple of months. The first two articles develop the interface between the probabilistic and the geometric models. First, the basic theory in 3 dimensions, and then the higher dimensional case, which has different properties. The third article develops the logic, which I call a manifold logic, because it is based on the differential manifolds that are defined in the first two. I will say a few words about each article. Here is the basic theory. This is a probability density in 3 dimensions, and you are looking at a 2-dimensional surface of constant probability. We imagine that this probability density was generated by a stochastic process, technically a diffusion process with a drift vector. Here is the vector field for the drift. Think of these arrows as pushing the probability mass towards the origin, counteracting the tendency of the diffusion process to flatten out the probabilities. When the system is in balance, we have a steady state solution, which is exactly the probability density shown on the previous slide. We are going to use this vector field to define a rho theta coordinate system for our geometric model. The radial coordinate, rho, will follow the vector field, and the directional coordinates, theta, will be orthogonal to it. This is what the geometric model looks like. It's a Riemannian manifold with a dissimilarity metric that measures increments of equal probability along the rho coordinate curves, and with theta coordinates that are geodesics, or shortest paths along the surface of constant probability density. I call this prototype coding. I could say a lot more about this model and prove theorems about it, but the most important general point is that the geometry matches the probability exactly, so that our calculations and constructions in the geometric model correspond to propositions about probabilities. Here we are generating data from the probability distribution and projecting it along the rho coordinate curves to the surface of constant probability. I am using a technical term on this slide, Frobenius integral manifold. That refers to a remarkable theorem from the 19th century differential geometry that makes all this work. You can see some clustering in these data points, but let's now look at some higher dimensional spaces and the clustering of the data points on lower dimensional submanifolds. This is from my second article, which analyzes 2 standard image processing examples, MNIST and CFAR10. The 7x7 patch is a 49-dimensional data point, and each one of these prototypes has a rho theta coordinate system defined around it. But now there are 48 theta coordinates, and we are looking for a small subset of these coordinates that still provides a good representation of the data. Look at prototype 9, the second patch in the second row. I won't go through the details, but you can probably see that we have reduced the dimensionality of these prototypical clusters from 49 to 12, consisting of the rho coordinate and 11 of the theta coordinates. Finally, deep learning. The previous slide depicted the operation in the lower right corner of this diagram, producing a 12-dimensional submanifold. Put 4 such manifolds together to form a product manifold with 48 dimensions, encoded as a 12-dimensional submanifold again and again and again, and finally categorize it as a digit 4 in the top row. The next slide will explain the step to manifold logic. This is the top line from the previous slide. We are forming the product manifold from the 4 patches and then constructing a submanifold for the digit 4. Here is the translation into a logical predicate. In classical logic, a predicate is a subset of the Cartesian product of its arguments. In a manifold logic, we are just replacing sets and their elements with manifolds and their points. And we can do this with any predicates. My choice was to develop this system as a higher order logic programming language, which is differentiable because everything in the logic is either a manifold or a smooth mapping on manifolds. You may have noticed that I have not said anything yet about law until I slipped in this reference to control, but these ideas actually go back to my early work on Taxman, especially my work on Taxman 2. Here are 3 principles from that work. 1, legal concepts are open textured. 2, legal rules are dynamic, so legal reasoning is primarily theory construction. 3, legal argument is, therefore, adversarial theory construction. My proposal to model all of this was to use prototypes and deformations, nicely illustrated by Justice Brandeis's opinion in Eisner versus Macomber. But the implementation was cumbersome, and we have a better model now with prototype coding and Riemannian dissimilarity metrics. This illustrates an old maxim: AI is an instrument to help us understand the law, and the law is the best domain we have to help us understand AI. That concludes my remarks. Thank you.
Thank you, Thorne. And now let us turn it over to Anne for some short remarks.
Thank you very much for the honor of this award, which I really would not have expected, but I'm very pleased by. At this point, I think I have just a couple of items where I want to suggest we still need some more work. There are some problems out there that we started out with, as far as I know, are still not anywhere close to solving. So let me go back to my thesis project. The original question was, can you get a computer to do legal reasoning? And the task I chose to work on was law school exam questions, where the facts are given and the student is supposed to write an essay answer analyzing their legal consequences. The program produced a data structure that identified the issues on which the decision in a court case could go either way. And I think probably the main thing that came out of this was, as has been mentioned, making everybody aware of open texture. There were a couple of possible next steps which did not get implemented. And one would have been to follow up on the issues that had been identified by the program by way of argument and case-based reasoning. And a lot of people have worked on that since. Another possible next step would have been to broaden the class of cases that the program could deal with, because the initial class was very, very narrow. And that would have required a couple of things. One was a more flexible control structure, and the other one was a bigger vocabulary, because every new problem you tried to encode would have new concepts that hadn't been used in the previous problem. So all of these concepts, the vocabulary, may be open textured, but some of them are harder to handle than others. And in particular, I'm thinking about propositional attitudes, intending that, believing that, knowing that, saying that, and so on. And these have caused philosophers a lot of trouble, and I don't know that we're any farther along with them now, but they definitely need someone to concentrate on them. The other item comes from the next project that I worked on, and it's the great contrast between the experience of working on an AI program and working on a real case, which happened to be big and complicated and technical. The case was between the United States and the state of Alaska, and it was filed in the Supreme Court, which you can do in certain cases. The general question was which government owns the lands just off the north coast of Alaska, the state or the federal government. And it mattered because that determined which government got to decide whether to open those lands for offshore oil exploration and possibly drilling. Now, the way the Supreme Court handles such cases is to appoint a special master. And in this case, it was a Stanford law professor that I had known for a long time. And my job was to help him write the report that recommended to the Supreme Court how they should decide. So in this case, now there were a few parts that fit quite nicely into our picture of what AI programs could do. For instance, one issue was, does this particular geographic feature count as an island? And I thought this really fits Thorne's prototypes and deformations approach. And there was another one involving whether a particular feature counted as a bay. And parts of that would have worked very nicely with Kevin Ashley's HYPE program, I think. But there were, other parts of the case, though, were not very much like AI programs at all. And the problem I'm particularly thinking of is working with statutes and other authoritative rules like a treaty, regulations, constitution, of course, and where a collection of these rather than just a single statute. A good deal has been done with encoding a single statute, but not so much with a collection of rules. And here they've been adopted at different times and in different situations, and somehow they all have something to do with the case. So how do we go about putting these rules all together to reach a sensible answer? And I hope people will look at that. I have a couple of papers on ResearchGate, not very recent, but they just are a bare beginning at trying to explore some of that. So I hope other people will continue. Thank you very much.
Thank you, Anne. Please join me one more time in congratulating our CodeX Prize winners, Thorne McCarty and Anne Gardner. Congratulations. Thank you. We now move to lunch, and please rejoin us at 1:30 for our next session.